In this lecture, we'll learn about decision trees. A brief outline. We'll first go over what a decision tree actually is. We'll then understand how decision trees work in order to understand its strengths and weaknesses. From there, we'll build decision tree classification models using the scikit-learn library. As far as where we are in the machine learning universe, decision trees can be used for classification and regression problems. A decision tree is a supervised learning algorithm, which is essentially a series of questions designed to assign a class or value. A decision tree used for classification is called a classification tree. A decision tree used for regression is called a regression tree. Some of the benefits of decision trees include: they're highly interpretable, predictions fast, they can be used for either classification or regression, and I should note that a lot of algorithms can only be used for one or the other. Decision trees work pretty well in nonlinear settings, and decision trees also don't require feature scaling. We'll get into feature scaling in later lectures. As far as flaws, without pruning or cross-validation, they're prone to overfitting. Small variations in the data can result in completely different trees, and they don't work well with highly unbalanced classes. If you don't understand this benefits and flaws section, we'll go into more detail about what some of these terms mean, like cross-validation or unbalanced classes, etc. What you see on the right side of the screen is a classification tree designed to classify one of 3 flower species. You may have already seen decision trees in your day-to-day life. This decision tree appeared in the New York Times, and it breaks down which county voted for either Obama or Clinton in a particular election cycle. I encourage you to pause the video and look at this decision tree. So decision trees for classification are called classification trees, and they are designed, like they sound, to assign a classification. If you look at the image on your right, the brown is a root node, and this is just the topmost decision node, and this is where you start traversing the classification tree. The leaf nodes, in green, are also called terminal nodes, and these are nodes that don't split into more nodes. And leaf nodes are where classes are assigned. Let's get into how to actually use a classification tree. So we start at the top, also known as the root node, and we ask a series of questions until we reach a terminal node. So with this image, imagine you had a flower with a petal length of 4.5 centimeters and you want to classify it. You first ask, is a petal length less than or equal to 2.45 centimeters? This statement is false because our petal length is 4.5. So we go to this decision node. We ask another question, is a petal length less than or equal to 4.95? This happens to be true, so we go to this leaf node or terminal node. The prediction in this terminal node is versicolor, as it is the majority class. Let's now get into the details of how these trees work. A tree learns a sequence of if-then questions, with each question involving one feature and one split point. So if you look at the partial tree to the right, the question petal length less than or equal to 2.45 splits the data into 2 branches based on some value. The value between the nodes is called a split point, and this particular split point value is 2.45. In part B of the figure, all the points to the left are classified as setosa. All the points to the right are classified as versicolor. The setosa was correctly classified for all 38 points. As you see here, we had 38 setosa and 0 of the versicolor or virginica. Since it's a pure node, it's not further classified, and impure nodes, like the one on the right here, can split further. This is because classification trees are a greedy algorithm, which means it'll continue to split until it has a pure node unless you stop it. So here's an additional split, and this tree so far has a depth of 2. The problem is that with many splits, it can lead to a very deep classification tree with many different nodes. This often leads to something called overfitting on the training set. One note about scikit-learn and decision trees in general is that most classification tree implementations allow you to control for the maximum depth of a tree. And the image on your right, this is just showing a visual representation of depth. As far as how decision trees decide to split on which feature and which split point, they split on the feature and split point that results in the largest information gain. There are 2 criterion that we'll examine, Gini and entropy. We can loosely define information gain for a given criterion as information before splitting of the parent node minus information after splitting, in other words, the children nodes. And in this image here, A is the parent node of the child nodes B and C. Part of the reason why I'm not emphasizing selecting one criterion versus another is that oftentimes they don't matter so much. One method to make your trees more effective models is to prune the tree, as this usually has a greater impact than impurity measures like Gini or entropy, and we'll see more of this soon. One benefit of using a decision tree versus other models is it's relatively easy to get your feature importance. In other words, what feature is most predictive, at least in theory, of your model. Classification trees in scikit-learn allow you to calculate feature importance, which is the total amount that Gini or entropy decrease due to splits over a given feature. Scikit-learn, as you see on the right side of your screen, outputs a number between 0 and 1 for each feature. All feature importances are normalized to sum to 1. As we'll see in the notebooks for this lesson, it's important to keep in mind that if a feature has a low feature importance value, it doesn't necessarily mean that the feature isn't important for prediction. It just means that that particular feature wasn't chosen at a particularly early level of a tree. It could be that the feature could be identical or highly correlated with another feature. The reason why I mention this is that understanding how metrics that come from your model work can not only improve your machine learning understanding, but help you make better models in the future. Decision trees can also be used for regression. Decision trees used for regression are called regression trees. Instead of returning a class, their leaf nodes return a single numeric value. Regression trees are in a lot of ways similar to classification trees. Some of the main differences are that they predict a continuous response, they predict using a mean response of each leaf, and splits are chosen to minimize mean squared error, typically. Another benefit of decision trees is that you can create a tree diagram of your model. You can do this by using the GraphViz library, and here's an image that outputs from GraphViz. You can also use the dtree library, which also requires GraphViz. And using GraphViz can sometimes be a bit challenging for students. Luckily, there's also a way to create a tree diagram with matplotlib. In this notebook, we're going over TrainTestSplit and decision trees. The rationale is that decision trees are often low bias and high variance, and so they are particularly susceptible to overfitting on the data. TrainTestSplit and cross-validation are procedures that estimate how well a model is likely to perform on out-of-sample data, and this will help us in tuning and choosing our models. As usual, the first thing we have to do is import the libraries that we're going to use. The first thing you see here is that we're importing pandas, numpy, and matplotlib. We're also going to import our decision tree, as well as something called tree, which we'll get to later. We're also going to import TrainTestSplit, k-fold, and cross-validation score. We're going to load the iris dataset. We're going to create our feature matrix. We're going to call this X. We're going to create our target vector, and we're going to call this Y. The thing that we've been doing, including in this first part of the notebook, is we're going to train and test on the entire data set. We've been doing this so far as a convenience, but it's actually a bad practice. And so to use a decision tree, it's the same process that we learned for linear regression, where you import the model that you want to use, you make an instance of your model. In this case, I'm saying that I want the maximum depth of the tree to be 5. I'm training the model on the entire data set and then making predictions. From here, we're measuring model performance. And there's many different ways to measure model performance, and we'll get to those. But for now, we're just doing accuracy, which is defined as the fraction of correct predictions over the total number of points. And you may wonder, why are we doing this train test split thing if our model score is 100%? And here's why. There are some problems with training and testing on the same data. The goal of building a model is oftentimes to create good performance on out-of-sample data. Maximizing the training efficiency rewards overly complex models that won't generalize. And unnecessarily complex models tend to overfit the training data. And here's an image of overfitting. This model looks like it may do a really good job of separating out one class in blue from the other, but would this actually fit a different sample of the data? Let's now go over train test split. And this is mostly what we'll be doing in this class. The first step is to split the data into 2 pieces, a training set and a testing set. And we're going to train the model on the training set. We'll then test the model on the testing set and evaluate how well we did. What this will accomplish is that models can be trained and tested on different data. We treat testing data like out-of-sample data. Response values are known for the testing set, and thus predictions can be evaluated. In Python, we'll be splitting our data into the training set and testing set using something called the TrainTestSplit function. You can see what this does if you use the help function on TrainTestSplit. The image shows a potential train test split for our data set, where it looks like a good part of our data is in our training set. If this looks a bit weird, I encourage you to review tuple unpacking. I'm looking at the shape of our features matrix. And then notice that the shape of our x_train is 120. This is because 80% of our data is in our training set. Similarly, you notice that the shape of our testing set is 30. So 30 over 150 is 20. So roughly 20% goes into our testing set. From here, it's the same process as before, where we're building a model and making predictions. And if you notice, our accuracy score here is lower than if we just trained on the entire data set and then made predictions on the entire data set. And as we discussed, that's a bad practice. So this accuracy score is probably more accurate for out-of-sample data. So with any sort of procedure, there's always benefits and disadvantages. One advantage of the train test split is that it's relatively fast, it's simple, and computationally inexpensive. One of the disadvantages is that we're losing some information to train on. As before, we were training on 100% of our data, and now we are training on 80%. Another method is cross-validation, and this better utilizes our data for training, as we can use more of it. Here's the procedure. The first step is to split our data into k equal partitions. So if k equals 5, and the dataset has 150 observations, like the iris dataset, each of the 5 folds would have 30 observations. We use one fold as a testing set, and the rest as a training set. So our testing set has 30 observations. We call that fold 5. And the training set has 120. And we call that fold 1 through 4. You calculate the training accuracy. So this is very similar so far to the train test split. The major difference is that we're repeating step 2 and 3 k times, using a different fold as a testing set each time. So in the second iteration of this process, fold 4 would be the testing set. A combination of fold 1, 2, 3, and 5 would be the training set. In the third iteration, fold 3 would be the testing set, and a combination of fold 1, 2, 4, and 5 would be the training set, and so on. From here, we're averaging all test accuracies to get estimated out-of-sample accuracy. Although this may sound complicated, we are just training the model on k-separate train test splits. This is more computationally intensive than train test split. Here's an image of 5-fold cross-validation. This code is a process similar to the image in the previous section. And what this code over here is doing is it's just doing this process for us. To reiterate the points in this notebook, an advantage of cross-validation relative to train test split is we get a typically more accurate estimate of out-of-sample accuracy. It's also a more efficient use of data in that every observation can be used for training and testing. An advantage of train test split relative to cross-validation is that it runs k times faster than k-fold cross-validation. So instead of training the model once, like train test split, k-fold cross-validation, you can train your model k times. So in some cases, you're training your model like 5 or 10 times. Another advantage is that it's simpler to examine the results of the testing process for a train test split relative to cross-validation. This next notebook is an exercise I want you to try. The goal of this exercise is to predict survival based on passenger characteristics for the Titanic. In the dataset, a 1 is survived and 0 is not. As this is a decision tree exercise, please use a decision tree model to accomplish this goal. It's important to keep in mind that you could use a bunch of different classification algorithms to accomplish this task. Let's now go over the solution. So as usual, we're inputting the libraries that we want to use. We're also going to input our data into a pandas data frame. The first thing to notice is that we're predicting the survive column, and the rest of the columns are our features. We're now going to arrange data into a features matrix and a target vector. Here are 4 columns I chose for my features. Of course, you could have chosen other columns. It's important to note we have a couple of categorical variables. A lot of categorical variables are not easy to directly input into your model. So what this code is doing is we're transforming the male and female strings in the sex column to a 0 and 1 respectively. and then we're reassigning it back to the original column. This code is a different way you could have accomplished the same goal, and I've commented it out using 3 quotations. Some of the values are actually missing in the age column, and most models do not deal well with NaN values. So you could have either imputed the values in the code over here, which I commented out. I imputed it with the mean. This could introduce error. What I ended up doing, and this is not a perfect approach by any means, is remove the rows where age is NaN from the dataset. And so finally, we're creating our X, our features matrix, and our Y, our target. From here, we're splitting our data into training and testing sets. We're next going to fit a classification tree. So we're going to import the model. We're going to make an instance of the model. You could have chosen different hyperparameters here. I'm just making the depth 3. We're next going to train the model on the data, and the model is learning the relationship between our features, in other words, the passenger characteristics, and our labels, whether they survived or not. Next, we're going to predict labels of new passengers. And what the code over here is showing is our classification accuracy. In other words, how accurate our model is at predicting survival. And one important point to mention is that oftentimes you compare your testing accuracy to the null accuracy. Null accuracy is usually considered the accuracy obtained by always predicting the most frequent class. And when interpreting the predictive power of a model, it's best to compare it to a baseline using a dummy model, sometimes called the baseline model. This is really important because say your dataset is really imbalanced. If it contains 99% to one class and 1% to another, then your baseline accuracy, always guessing the most common class, would be 99%. And if your model is less than 99% accurate, you know it's worse than the baseline. There are a lot of different ways to deal with imbalanced datasets, and this is just something to keep in mind. For our dataset, we have 103 people that didn't survive and 76 that did. If you just guessed that everyone didn't survive, your model would be 57.5% accurate. And the model that I just trained in this notebook has an accuracy of 78%, so it's better than the null accuracy. This section of the notebook is just going over a confusion matrix, which is often used to assess the performance of a classification model. This code is just creating a confusion matrix. This confusion matrix is showing 99 times we predicted a 0 when it was actually a 0. We predicted 35 times that someone didn't survive when they actually did, and so on and so forth. One of the benefits of a decision tree is that it allows you to calculate the feature importance, which is the total amount that getting index or entropy decrease due to splits over a given feature. And a number is assigned between 0 and 1 for each feature, and a feature importance of 0 means that the feature was not used in prediction. For the model that I built, sex was the most important feature according to feature importance. One of the benefits of a decision tree model is that they're interpretable In other words, you can understand how a prediction was made. And in scikit-learn, there's a way to output a decision tree image. This is a relatively new feature, and you're just doing tree.plot_tree. You have your feature columns. You have whether someone lived or didn't.